13.75 billion years ago the universe began. Why we don't know. 380,000 years after the Big Bang. It's a very precise number. You might say, how do you know that? Well, before that time the universe was so hot that atoms couldn't form, so you had a soup of electrically charged particles. It's just too hot for electrons to go into orbit around nuclei, so the universe was opaque to light, so you just couldn't. It's like almost like a big glowing star if you like. What if I told you that our universe has existed indefinitely, even preceding the Big Bang? It might sound quite extraordinary. Hold on to your hats, because acclaimed physicist Brian Cox is embracing this mind-boggling concept, music. It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology if you like, but the current textbook picture is there was a phase in the universe's life before the Big Bang. If you define the Big Bang as the hot dense phase from which the universe appeared to sort of burst for 13.8 billion years ago, and that phase is called inflation. So what we think happened is that before that the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size, and the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe. 350 billion galaxies in it in less than a millionths of a second. So very rapid, exponentially fast expansion, and when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which were made and all the things that we see out there in the sky, and that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stops the inflation? How long did the inflation go on for? And the answer to that is we're not sure. We don't know. There are theories now that suggest, as I mentioned, that there may be more than one universe and potentially an infinite number. It's a mind-boggling idea, isn't it? And I should say one extra thing: if that's true, then some of those theories say that what we call the constants of nature, so things like the strength of gravity, the speed of light, the masses of the particles, can vary from universe to universe. And then you ask the question, well, why is our universe so perfect for life? Why do stars make carbon and oxygen, the elements that you need for life? Why is everything so beautifully balanced so that living things can exist? The answer in these cases is because, well, every universe exists. Every possible combination of the laws of nature exists in different universes. So the reason we have to see a universe that allows us to exist, obviously we could ask the question, well, how likely is that? Well, the answer, if there are an infinite number of them, is it's inevitable, because there's every possible kind of universe. And I stress that this is very speculative stuff. But the first thing I said about inflation, the idea there was this exponentially fast expansion before the Big Bang, if you want to use that language, that's not speculative, that's mainstream cosmology. This idea that that may lead to multiple universes is more speculative, but it's still scientifically valid, and there are people who do research into that. And again, this is an active area of research in the grand tapestry of the cosmos. Nestled amidst the vast expanse of time and space lies a notion so profound, so paradigm-shifting, that it challenges the very foundations of our understanding. It is a concept born from the brilliant mind of Sir Roger Penrose, a luminary in the realm of theoretical physics, and now embraced by none other than the esteemed physicist Brian Cox. This concept, known as conformal cyclic cosmology (CCC), proposes a breathtakingly audacious idea that our universe is not an isolated entity, but rather one iteration in an infinite cosmic lineage. Picture this: a universe not bound by the constraints of a singular beginning and end, but rather existing in a cyclical dance of creation and destruction, stretching back into an unfathomable abyss of time. Penrose's theory suggests that our universe may have emerged from the remnants of a previous one, setting in motion an eternal cycle of cosmic rebirth. It challenges our conventional understanding of time and space, presenting a vision where beginnings and endings are not absolute, but rather part of an endless continuum. The recent revelations from the James Webb Telescope serve as a testament to the tantalizing possibilities of Penrose's CCC. Among its myriad discoveries are galaxies and black holes that defy the conventional timelines of cosmology, existing mere moments after the cataclysmic event known as the Big Bang. One such discovery, a galaxy bearing a striking resemblance to our own Milky Way, raises profound questions about the early evolution of cosmic structures, suggesting that galaxies may have formed much earlier than previously believed. At the heart of Penrose's CCD lie the enigmatic Hawking points - tiny remnants of black holes from previous universe cycles imprinted within the cosmic microwave background. These points serve as cosmic fossils, offering glimpses into the epochs that preceded our own. They hint at a universe far more ancient and interconnected than we ever dared to imagine, where the echoes of past cycles reverberate throughout the fabric of space-time. But perhaps the most compelling evidence in support of Penrose's theory comes from the discovery of ultramassive black holes near the dawn of time. These cosmic behemoths with masses exceeding 1 billion suns challenge our understanding of how such structures could have formed so rapidly after the Big Bang. Their existence lends credence to the idea that information from one universe can seamlessly transition to the next, as if carrying the memories of past epochs forward into eternity. As we delve deeper into the mysteries of the cosmos, Penrose's CCC beckons us to confront profound questions about the nature of existence itself. It invites us to contemplate the possibility of a universe without beginning or end, where time flows in a perpetual loop of creation and destruction. In doing so, it forces us to reevaluate our place within the vast cosmic tapestry, reminding us that our understanding of reality is but a fleeting glimpse into the infinite depths of the cosmos. Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies, etc., etc. So the way in which inflation explains the Bang is, in terms of a very surprising feature of physics, I think very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity, but that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively, and furthermore modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsive form of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity. Once you decide that this mechanism of propulsion is very likely the way our universe was born, you can ask, what kind of universe does it predict, and does it agree with what we see and in fact allows us to understand three very important properties of our universe. One is it allows us to understand the uniformity of our universe. As I think was already mentioned, this cosmic background radiation that has been now measured with incredible precision has fluctuations which are incredibly interesting, and we'll be talking about them tonight. But these fluctuations are incredibly tiny. They're only at the level of 1 part in 100,000 to an accuracy of 1 part in 100,000. The cosmic background radiation that we see is the same intensity in every direction that we look. The universe is just unbelievably uniform on large scales, and that cannot be understood in the conventional Big Bang picture. But inflation explains it very naturally. You start with a very small universe which becomes uniform before inflation, and then inflation just takes over and magnifies this tiny uniform speck to become large enough to include everything that we observe. In the 1980s, the groundbreaking theory of inflation emerged, revealing that shortly after the Big Bang a minute portion of space underwent rapid expansion due to a phenomenon called inflation. This expansion, akin to balloon inflating, smoothed out initial irregularities, laying the groundwork for the observable universe we know today. However, the concept of eternal inflation suggests that this process continues indefinitely in certain regions of space, forming bubble universes, while in others it persists, potentially generating an infinite array of universes. This notion introduces the concept of a multiverse, wherein countless universes exist with varying physical laws and constants within this expansive framework. Further inflation may occur as the bubbles expand, contributing to the growth of the multiverse. Universes interact within this complex web, and inflation gradually decelerates this depiction of the multiverse as a realm of continuous evolution and creation, gives rise to the concept of a cyclical universe, highlighting constant renewal and expansion on a grand scale. Analogously, one can envision Earth as a microcosm of this multiverse, teeming with diverse life forms and habitats that undergo continual change and renewal, just as individuals, animals and seasons come and go on on Earth, new universes may emerge within the vast expanse of the multiverse, perpetuating a dynamic cycle of existence and growth. Eternal inflation and the multiverse fundamentally reshape our understanding of time and space. While the theory of relativity views time and space as components of a four-dimensional continuum influenced by mass and energy, the multiverse introduces a level of complexity that stretches the limits of our current scientific tools. The quest for a unified theory, akin to Albert Einstein's pursuit of a singular equation encompassing everything the universe comprises, remains elusive. Scientists continue to await the discovery of this mystical formula, often referred to as the unified field formula. Perhaps our approach, focused on narrow fields of study, obscures a broader understanding of the universe, akin to examining a single leaf to understand the entirety of a tree. As we delve deeper into the realm of particle physics, the enigmatic nature of subatomic particles becomes increasingly apparent. Despite our technological advancements and observations spanning vast distances, our understanding may be akin to a single grain of sand on a last beach. Black holes, pivotal entities in the universe's formation, raise intriguing questions about their role as potential inaugural entities. Astrophysicist Neil deGrasse Tyson suggests that the James Webb Telescope's detection of black holes from a previous universe could indicate a cyclical nature of cosmic rebirths, challenging our understanding of cosmology. The discovery of ancient G-galaxies and black holes by the James Webb Space Telescope raises questions about the universe's age and the formation of matter. Quantum physicists speculate about the origins of matter, suggesting that the universe emerged from a state of absolute equilibrium leading to the Big Bang and the formation of subatomic particles. Roger Penrose's conformal cyclic cosmology presents a compelling idea: an unending succession of PHS, each kick-started by a Big Bang and culminating in a state akin to a fresh inception. This theory appends conventional notions of time and space, advocating for a cyclical process that endlessly repeats itself, shaping the universe's narrative in an unprecedented manner. In this cyclical model, the absence of a space-time singularity at the inception of each implies a timeless origin of time emerging as a consequence of cosmic evolution rather than having a definitive starting point. This perspective reshapes our understanding of the universe's origins and evolution, inviting further exploration into the mysteries of time, space, and existence. It challenges traditional notions of a linear timeline and encourages a deeper investigation into the fundamental nature of reality, offering a framework that encompasses both continuity and renewal on cosmic scales. Thank you for watching another episode of CCO TV. While you are still here, don't forget to like and subscribe. 30